What if the first sign of life we find on the moon isn't alien at all? What if we brought it there ourselves? A new NASA study suggests some Earth microbes could survive if carried to the lunar South Pole. That doesn't mean NASA found life on the moon. They wouldn't need to grow or reproduce, they would only need to survive. Because if future lunar samples contain signs of life, scientists will face a difficult question. Did it come from the moon or from us? Spacesuits, equipment, habitats, even our skin. When humans enter another world, we never arrive alone. We bring an invisible ecosystem with us, and strangely, the darkest places near the lunar South Pole may help some microbes persist. Inside permanently shadowed craters, sunlight barely reaches the surface. It's brutally cold. But for dormant microbes, that darkness removes one of their greatest threats: solar ultraviolet radiation. These are permanently shadowed regions. Near the lunar poles, the sun stays low on the horizon, and crater walls can keep some floors out of direct sunlight for immense spans of time. That sounds like a dead zone. But for a dormant microbe, less ultraviolet exposure can mean more protection. NASA did not put living microbes on the moon. Researchers combined tolerance data from 5 microorganisms with environmental maps of the lunar South Pole. The model produced a strange result. Possible survival niches range from crater floor patches to areas as small as an astronaut's footprint. Among the organisms tested, Aspergillus noyi, a fungus seen in spacecraft environments, showed especially strong ultraviolet tolerance. But this is still a model. It is not evidence that living microbes have been found on the moon. The real question is what happens next. If even a tiny sheltered patch could preserve terrestrial life, how much might an entire lunar base bring with it? The hardest thing to sterilize is not the base. It's the people inside it. Spacecraft hardware can be treated aggressively. Heat-resistant parts can be baked. Other components can be cleaned with chemical methods, ultraviolet light, and strict clean room procedures, but you cannot turn a living human into sterile equipment. Our skin, breath, sweat, and shed cells all travel with microbial passengers. A spacesuit helps. But a crude habitat is not a sterile jar. People breathe, eat, exercise, sleep, and touch equipment every day. On the International Space Station, microbes are routinely detected, and many are associated with humans. So a lunar outpost would carry a small Earth ecosystem with it. That changes the question. It is no longer simply whether humans will bring biological material to the moon. It is how well we can document and control what we bring. Here's the counterintuitive part. The moon is not treated like Mars under planetary protection rules. The goal is not simply to keep the moon clean, it is to stop terrestrial contamination from confusing future science. Lunar missions fall within Category 2. Surface missions to polar or permanently shadowed regions are treated as Category 2B. Many Mars landers fall under Category 4. Those numbers are not a ranking of importance. They reflect different contamination risks. For decades, the lunar surface seemed too dry, too cold, and too irradiated for Earth microbes to persist. Mars raised a different concern. Terrestrial organisms might survive well enough to interfere with life detection experiments. But the lunar picture is getting more complicated. Permanently shadowed regions already carry stronger documentation requirements, and new modeling suggests some microbes could persist there. The rules have not been overturned. The risk boundary has simply become harder to define. And we have faced a version of this problem before. In 1967, Surveyor 3 landed on the moon. 31 months later, Apollo 12 touched down nearby. 2 astronauts walked to the spacecraft, removed parts of its television camera, and brought them back to Earth. Then came the surprise. Researchers cultured a living bacterium, Streptococcus amitis, from foam inside the camera. At the time, the interpretation was extraordinary. Perhaps it had entered before launch, survived 31 months on the moon, returned to Earth, and grown again in the laboratory. But later reviews raised a serious problem. There were opportunities for contamination during recovery, transport, disassembly, and sampling. Records also raised questions about sterile technique, so the evidence cannot prove that the bacterium survived on the moon for 31 months. Earth-side contamination remains a strong alternative explanation, and that is why the case matters. If we cannot recognize our own contamination, how can we prove a future biological signal is truly lunar? Perfect sterility is not the answer. For crewed missions, it is unrealistic. The practical goal is to know what we brought with us. NASA uses the term contamination knowledge. What materials were used? Which microbes were present in clean rooms? What compounds were found on spacecraft surfaces? The more we record before sampling, the more context we have later. Some sample missions also use witness plates. They share the sampling environment and record contamination along the way. If a returned lunar sample contains an unusual organic or microbial signal, scientists can compare it with that archive. Have we seen this before? If yes, terrestrial contamination becomes a strong suspect. If not, that still does not mean lunar life. It only means the source remains unexplained, and that raises another question. If life is not expected to flourish on the lunar surface, what are we actually trying to protect? Possibly not life at all. Scientists may be protecting a chemical archive preserved for immense spans of time. Cold traps near the lunar south pole may hold more than water ice. They may also preserve carbon dioxide, methane, and other volatiles. Where did they come from? Some may have arrived with asteroids or comets. Others may be linked to the solar wind, while some could come from the moon's interior. So the question isn't simply, is there ice here? It's what history may be recorded inside it. An archive does not have to be destroyed to lose clarity. It can be overwritten. A lander's exhaust introduces new gases and volatiles. Some may settle into the regolith or reach cold traps, add spacecraft materials and human activity, and later measurements become harder to interpret. Are we seeing lunar history? Or something humans left only a few years early? That is the paradox. We go south because the ice is valuable. The same lunar ice has two identities. To scientists, it is an ancient sample. To a future lunar base, it is also a resource. Water could support crews split into hydrogen and oxygen. It could provide life support oxygen and potentially ingredients for propellant. NASA calls this in situ resource utilization, or ISRU. Use what is available locally instead of carrying everything from Earth. It sounds reasonable, and that is where the tension begins. To learn how much ice exists, how deep it is, and whether it can be used, missions may need to drill, sample, and excavate. But those actions can alter the environment scientists most want to study. For the same patch of ice, science benefits from minimal disturbance. Resource use requires contact. That is the contradiction at the lunar South Pole. The more we want to understand it, the closer we have to get. And the closer we get, the more we may leave behind. Microbes, engine exhaust, organic compounds, a footprint, a machine, perhaps one day, an entire base. So, the hardest question may not be, did we find life on the moon? It may be, how do we prove the answer was already there? We go to the moon to search for answers, but exploration itself can change the answer.